Hello again. We've moved on to the second week of our course, and we're already up to the first exam. The first exam will be posted online on Tuesday the 9th at approximately 9 in the morning, and you will have 24 hours to complete it. It will be 4 questions. The first exam only covers the first 2 chapters. All the subsequent exams, which will be in 2-week intervals from today. It will be in 2-week intervals the rest of the semester, but the subsequent exams will cover 3 chapters each. This only covers 2 chapters, so the exams will, this exam will have 2 questions from each chapter. So there'll be 2 on chapter 13, and there will be 2 on chapter 21. So I want to start by reviewing chapter 13. So for chapter 13, we talked about fluids, and fluids are liquids or gases. So, I mean, traditionally when we think of fluids, we think of them as liquids, but gases apply as fluids as well. Basically, a fluid does not have a defined shape, and it can flow. It can spread around. It's it's not confined to a particular spot. If you're exerting no forces on it. So the first general property of fluids that we talk about is density. And density is a convenient quantity when talking about fluids because it's not always easy to measure the mass or to measure the volume directly. In fact, often you're talking about an arbitrary size of whether if you're talking about the air or a subset of the air or a subset of the water, you're talking about an object of an arbitrary size. So you don't have a specific mass or a specific volume, but the ratio is something that you can talk about, and that's the ratio of the mass to volume, and that's what density is. And the gram was initially defined as the amount of mass contained in 1 cubic centimeter of water. So when we talk about water, its density in terms of grams per cubic centimeters is 1. In terms of kilograms per cubic meters, it's 1,000. So the definition of the kilogram and the definition of the meter have evolved from their original definitions when the metric system was first developed. But the basic value, certainly to the precision that we need of 1,000 kilograms per cubic meter, remains unchanged for the density of liquid water. And the density of air is quite a bit more variable. What you'll find is that the density of liquids tends to be constant unless you make very extreme changes in temperature or pressure. Whereas with a gas, even a slight change in temperature or pressure will affect the density. So at 0 degrees Celsius at sea level, the density of air is 1.29 kilograms per cubic meter. But the global mean density for the air at sea level is 1.22 kilograms per cubic meter. In general, the Earth is warmer than 0 degrees Celsius. The average temperature on the Earth's surface is 15 degrees Celsius, or about 59 degrees Fahrenheit. And so that expands the air, which lowers the density. And again, with solids and liquids, density doesn't change a whole lot with temperature and pressure. It does change a little, but not, it takes a very substantial change in temperature or pressure to produce a noticeable change in density. But with gases, it's very easy to change the density. It varies very noticeably with changes in temperature and pressure. Another term that you see sometimes is the specific gravity, which is the ratio of an object's density to the density of liquid water. It's not as important in metric units, and for the most part, we'll be working with metric units. In the SI system is essentially based on the metric system. So the density in grams per cubic centimeter is going to equal the object's specific gravity. But again, in formal SI units, the density is measured in kilograms per cubic meter. There are a number of different density, objects, and another important property of density is that it's substance specific, and we'll see that quite a bit in the rest of the semester when we're talking about electricity, that a lot of properties are substance specific. Each substance has a different value. And so you look at the metals, they tend to have a higher density than liquid water. Concrete and granite also have a higher density than liquid water. Wood has a lower density than liquid water, about 300 to 900 kilograms per cubic meter. One of the consequences of that is that wood floats in water, and we'll talk a little bit more about that when we get to Archimedes' principle. Notice that ice also is less dense than liquid water, and that's very important. Ice floats on water, it stays on the top, and it insulates the liquid water beneath it and keeps that liquid, keeps that from freezing. And that's very important. If ice were more dense than liquid water, the ice would sink to the bottom, and then the water at the surface would freeze and sink to the bottom, and pretty soon the entire body of water would be frozen, along with every living thing inside it. But that's not what happens, and that's very critical for the development of life. You look at liquids, blood is mostly water, so it's probably not surprising that its density is very similar to that of water. Seawater is more dense than fresh water. And I don't know if any of you have been swimming in the Dead Sea or the Great Salt Lake, but you know that it's easier to float in those bodies of water. If you've ever been in a saltwater pool, there are a few of those. It's easier to float in a saltwater pool than it is to float in a regular pool. And gases, you see, have quite a bit lower density. The densities of solids and liquids tend to be on the order of 10 to the 3 kilograms per cubic meter. For air, it's about 1 times 10, or it's about 1, no times 10 to the 3, so about 1 kilogram per cubic meter. The density of gases basically varies with the molecular mass of the gas. If you're talking about an ideal gas, its volume for a given temperature and pressure doesn't change with the substance. So that for an ideal gas at a given temperature and pressure, the density depends entirely on the molecular mass of the substance in question. So air is typically nitrogen and oxygen. Helium is much lighter than nitrogen and oxygen, so it's much less dense than the air. Hydrogen would be even less dense still than helium. Carbon dioxide is 2 oxygen atoms plus a carbon atom, so that's more dense than the air. Steam is 1 oxygen atom plus 2 hydrogen atoms, so that's less dense than the air. So from density, we move on to pressure. Pressure is the ratio of applied force per unit area. Pressure acts on an object from all sides, and an object exerts pressure out from all sides as well. The unit of pressure in SI units is the Pascal. It's 1 Newton per square meter. The average atmospheric pressure at sea level, or 1 atmosphere, is equal to approximately 1.01 times 10 to the 5 Pascal, which means that if you go to the beach and you draw a 1 meter square box, the air above that box, directly above that box, weighs 1.01 times 10 to the 5 newtons, or about 101,000 newtons. And that might seem like a lot of weight, but you have to remember we're used to living in that kind of pressure. So we only really notice it when the pressure changes. That if the pressure is what it normally is, we don't really feel it because that's what we live through and live with on a daily basis. But we do notice when it changes. So if you're driving up in the mountains and you're going up and down steep hills, you'll feel it in your ears first. And if you go scuba diving and where the water pressure is very high, you'll feel that. And if you come up too quickly, you'll feel that as well, the depressurization as well. That phenomenon is called the bends, and it's dangerous if you're not careful. Pascal, for whom the unit of pressure is named, came up with a principle that pressure change at any point in a confined fluid is transmitted throughout the fluid so that the same change occurs everywhere. It basically says that, this is true for a given height. And when we say incompressible, that means the density remains constant, which almost always applies to liquids. But so what that means is that the pressure at one location at a given height is going to be the same as the pressure at the same height at a different location. And if the height's not changing significantly, the pressure is more or less constant. And that has a useful practical application when you're talking about hydraulic lifting. So you can exert a small force over a small area pushing down, but the pressure you push down on the liquid, presumably water, then gets applied upwards at a different location. And if you have a much greater area, it's the same pressure that's going to apply, but the total force is going to be much greater. And that makes it possible for a relatively small force to lift an automobile, for example. And so you can turn a small force into a big force by doing that. Another application of Pascal's principle comes with the pressure of a liquid. And remember, we derived this in a previous lecture. And so the pressure of a liquid is equal to the density of the liquid multiplied by the acceleration of gravity, which is g. And at the Earth's surface, that's 9.80 or 9.81 meters per second squared. And so rho, the density, times g times h, which is the depth of the liquid. And so you can use that fact and Pascal's principle to measure the pressure of the air. You have an evacuated column that the liquid rises up into, but it's exposed to the air. So the air pushes down on the liquid, and then the liquid pushes up inside the evacuated chamber. And so the liquid gets pushed up into the evacuated chamber until the pressure inside the chamber, which is equal to rho gh, equals the air pressure outside. So you have the same pressure going from both ends when you're in equilibrium. And so you'll sometimes see the barometric pressure, the air pressure, defined in terms of inches of mercury. Well, that's the height of an evacuated column of mercury if the air is pressing down on it. And so, the density of mercury is 13.6 times 10 to the 3 kilograms per cubic meter. So it's much more dense, or they're quite a bit more dense than water. And so the air presses down. And if you know what the average air pressure is, and you take the density of mercury and the value of G, you can figure out the height that you would expect the mercury to go to. And in general, you would figure that out in SI units in meters, but if you convert that to inches, it's about 30 inches of mercury. And so that's where that measurement of air pressure comes from. Mercury was used because it's quite a bit more dense than water. You need a smaller evacuated chamber to get good results from it. However, mercury is very dangerous to handle, so when we're measuring air pressure, we generally don't use mercury now. And that brings us to Archimedes' principle. And this is one of the oldest principles in physics. It goes back more than 2,000 years. Archimedes was an ancient Greek who lived on the Isle of Sicily, which was regularly fought over. And he was an important military person at the time, but he's best known now for this principle. And that's that an object submerged in water experiences an upward buoyant force equal to the volume of water that would be in the object's place if it weren't there. And this applies to fluids in general, so it doesn't have to be water. But the net force acting on the object is equal to the buoyant force minus the object's weight. The buoyant force is equal to the density of the fluid multiplied by the acceleration of gravity g, multiplied by the portion of the object's volume that's under the that's below the surface, so that's submerged. If it's completely submerged, it's the entire volume of the object, but if it's only partially submerged, you're only interested in the volume of the object that's under the surface or underneath the surface. So the net force, again, is the buoyant force minus the object's weight. And you can write that as the density of the fluid times g times the submerged volume of the object minus the density of the object times g times the total volume of the object. And if the object is completely submerged, that net force becomes the difference between the density of the fluid and the density of the object times g times the volume of the object. And so what's the significance of that? Well, if the fluid is more dense than the object, the net force is positive, meaning it's upward, and the submerged object will rise to the surface and float. And if the net force is negative, if the object has a higher density than the fluid, the object will sink. The net force is negative, meaning downward, and the object will sink. So, the easiest way to tell if an object is more dense or less dense than water is to dunk it in water, let it go, and see if it rises back to the top or if it continues to sink. And that will tell you something about the density of the object relative to water. So that brings us to continuous flow. And in continuous flow, we went through this derivation. The mass of the fluid flowing past point 1 is going to equal the mass of the fluid flowing past point 2. And if the fluid is incompressible or it has a constant density, that means the volume of fluid floating past point 1 is equal to the volume of fluid floating past point 2. And the amount of fluid flowing past point 1 per unit time is equal to the product of the cross-sectional area multiplied by the velocity. So that product of area times velocity is a conserved quantity. So A1 V1 is equal to A2 small v2. So velocity is small v, and then the volume is capital V. So delta capital V over delta T, the volume of the fluid passing any point in the pipe over a time delta T is going to remain constant, and it equals the cross-sectional area multiplied by the velocity. So again, volume is capital V, velocity is small v. And not only is mass conserved in continuous flow, but energy is conserved. And so going back to physics 1, the work done is equal to the change in kinetic energy plus the change in potential energy. So there may be pressure on two ends of the pipes, and there may be a difference in pressure. And that difference in pressure causes a net amount of work to be done, which can be either positive or negative, depending on whether the pressure increases as you flow past or decreases as you flow past. But the pressure or the change in pressure, the difference in pressure, again, from the energy conservation equation, is equal to the change in kinetic energy per unit volume plus the change in potential energy per unit volume. And so you get the energy conservation is written like can be written like it is here. That P1, so the pressure at point 1, plus 1/2 rho V1 squared, the kinetic energy per unit volume at point 1, plus the potential energy per unit volume at point 1, rho Gy1, is equal to the pressure at point 2, plus 1/2 rho V2 squared, the kinetic energy per unit volume at point 2, plus rho Gy2, the potential energy per unit volume at point 2. So that was chapter 13. And so that's all we're doing with motion in this semester. Then we're moving on to chapter 21, which begins our study of electricity, which we won't entirely finish. Which we won't entirely finish this semester, but we'll get most of the way through it. We'll go all the way up to chapter 30. And like I said, we're moving a bit more deliberately in this class because we work in 3 semesters rather than 2 semesters. The difference is you see quite a bit more mathematics. And that's going to help you later on, especially if you're taking a more advanced electricity and magnetism course as you continue your as you pursue your bachelor's degree. But let's talk about the basics of electric charges. There are 2 types of charges. They're positive and they're negative. Like charges repel, so if you put 2 positive charges near each other, they will repel each other. They will push each other away. If you put 2 negative charges near each other, they will also push each other away. But if you put a positive charge and a negative charge near each other, they will attract each other. So like charges repel and opposite charges attract. At the atomic level, positive charges are carried by protons while negative charges are carried by electrons. Protons tend to be held firmly within the atomic nucleus. There is something called a strong nuclear force that at the atomic scale is stronger than electricity, and it allows the protons to be held together in the nucleus without being repelled by without them being repelling each other by the electrical force. One of the consequences of that is that it's much easier to move electrons than protons. So generally when we're talking about an electric circuit, it's the electrons that are doing all the moving. So on the big scale, the protons and electrons in an object generally cancel each other out so that there's not a charge. Sometimes it's possible to get a certain amount of electrons to move or to either come onto a substance, in which case it becomes negatively charged, or to be removed from a substance, which means it becomes positively charged. And the unit of electric charge is called the coulomb. Well, you'll have to wait till the end of chapter 28 to see how the coulomb is defined. So you'll have to accept the value as being what it is for the time being, and then we'll eventually get to defining it. But all the electrical, and it turns out all the magnetical units as well, and the electrical and magnetic constants that we talk about are defined or get their values from the definition of the ampere. And we'll see in chapter 28 how the ampere gets its definition. But certain products of electrical and magnetic quantities or constants do not depend on that value. And that becomes very important when you get to electromagnetic waves, which won't happen this semester, but you will see it eventually. So there are basically 3 types of substances where electricity is concerned. Conductors allow electrons to move easily, and when we think of conductors, we think of metals. Insulators do not allow electrons to move. It takes a lot. The electrons need to be supplied with a lot of energy in order to be able to move through insulators. But Uh, Insulators are typically like quartz or rubber or things like that. The air is a pretty strong insulator also. The last type of substance is a semiconductor, which allows some electrons to flow through it, or some amount of electrons to flow through it. And so silicon, germanium, and carbon are typically considered to be semiconductors. And semiconductors are very important in electric circuitry because they allow you to regulate the flow of current. And that makes it possible to have all the electric devices and appliances we have. So that's a very useful property. So conductors there are a couple of different ways to charge objects. You can charge objects by conduction, or you can observe charge by charging objects by conduction. So some sort of contact or friction allows electrons to jump from one object to another. So the object that gains the electrons becomes negatively charged. The object that loses the electrons becomes positively charged. And then you can put those objects near other charged objects and observe the attraction or the repulsion. Another way of observing electrical forces or electrical charges is through induced charges or polarization, in which case you're not changing the net amount of charge in an object, but if you hold a charged object near it, so if it's a positively charged object, the electrons in a neutrally charged object will move towards it. If it's a negatively charged object, it'll repel the electrons and they'll move to the other side. In both cases, you get what's called polarization. You get a positively charged side and a negatively charged side on what's otherwise a neutrally charged object, or where the net charge is zero. But you'll still observe attraction, so that if you hold a positively charged object, the electrons will come close, so the negatively charged side will be near the positively charged side, and you'll see attraction. And if you put a negatively charged object, well, that'll repel the electrons. And so you have a positively charged side near the negatively charged object, and you'll still see attraction. And so that brings us to Coulomb's law. So Coulomb, whom the unit of charge is named for, came up with a law that looks a lot like Newton's universal law of gravitation. It's an inverse square law. The r vector that you'll see, whether it's r hat, the unit vector, or r arrow with the magnitude included, the r vector points from the object exerting the force to the object that the force is acting on. And so mathematically speaking, if Q1 and Q2 are the same charge, the force is going to be positive in the direction of R, which means repulsion. So it's going from the object exerting the force or away from it into the object that it's acting on. And that's repulsion. But if either Q1 or Q2 is negative and the other charge is positive, then the product of Q1 and Q2 is negative, and so the force is in the opposite direction of the r vector, which is towards the object exerting the force. And that's attraction. So for Newton's third law, the objects are exerting equal and opposite forces on each other. And so the first way of writing it, you have the unit vector, and it's divided by r squared. So the magnitude varies by the inverse of the square of the distance between the two of them. And the second way of writing it is you have the vector r arrow, and it's divided by r cubed. But remember, r is the magnitude of r arrow. And so there's a slight distinction, but sometimes it's easier to write it the second way. And usually the more complicated the problem, the easier it is to write the equation the second way in order to solve it. So the term K is a proportionality constant, much like capital G in Newton's law of gravitation. It's a universal constant, and it equals 8.9875 times 10 to the 9 Newton meters squared per Coulomb squared. One way of thinking of it is simply 9 times 10 to the 9. And so that's an important universal constant. And again, if both charges have the same size sign, they will repel. If both charges have the opposite sign, they will attract. One important principle that comes into play sometimes in more complicated Coulomb's law problems, and also evaluating the electric field due to multiple source charges, and we'll talk about that in a couple of minutes, is the superposition principle, that the resultant vector is the sum of the individual vectors. So you figure out the individual force vectors, and then you add them together vectorially. So that's going back to vector addition and figuring out the resultant vector, which goes back to physics 1. And I'm assuming you've had physics 1, whether you had it here or someplace else. So you know what vector addition is. If you're having trouble remembering how vector addition works, now's a really good time to brush up on that. So then we move from electric force to electric field. Gravity and electricity are both field forces. The objects do not have to be in contact with each other to exert forces on each other. So they're not contact forces. They're called field forces. And so a charged object creates an electric field around it. And so we call the charged object, or the series of charged objects, a source charge or source charges. And you don't need to have another object moving within the electric field to have the electric field existing. You would need an object for the electric field to exert a force, but the field exists whether there's a force acting or not. And the concept of a field is useful in describing the motion of an object if the object's charge is small enough that it doesn't affect the overall electric field. So size matters. So to make the analogy with gravity, if you're talking about the motion of the Earth around the sun, well, the Earth's gravitational field is small compared to the sun's gravitational field. And so the motion of the Earth doesn't affect the sun's gravitational field all that significantly. So again, we have the source charges, which are the charges that create the electric field, and then we have a test charge, QT, that's moving within the electric field. But when we're talking about the magnitude of the direction of the electric field vector, we're only concerned about the source charge or source charges. So how do you relate the electric field due to the source charges to the electric force that's acting on the test charge? Well, vectorially speaking, F is equal to QT times E. So the electric force vector is equal to the test charge multiplied by the electric field vector, or the electric field vector is equal to the electric force vector divided by the test charge. So a couple of things come from that. One, QT can be positive or negative. There are no absolute value signs there. So if QT is a positive charge, the electric force vector and the electric field vector point in the same direction. So if the electric field vector is acting on, if the electric field is acting on a positive charge, the electric force is going to point in the same direction as the electric field. If the electric field is acting on a negative charge, the electric force is going to be in the opposite direction of the electric field. And the other thing we get out of that is that the electric field is equal to force divided by charge. So when we talk in SI units of the electric field, we're usually measuring it in terms of newtons per coulomb. We will find when we get to chapter 23 that you can equivalently express it in terms of volts per meter. But we're jumping ahead a little bit. But a positive test charge is accelerated in the direction of the field, while a negative test charge is accelerated in the opposite direction of the field. So for one source charge, the electric field due to that source charge can be written as K, the Coulomb constant, multiplied by the source charge, divided by r squared, and again, pointing in the r hat direction. So the r hat points away from the source charge. And you can also write that as kqs over r cubed times r arrow, where r arrow is the full vector whose magnitude equals the distance from the source charge to the point where the field is being evaluated. So what comes out of that is that the electric field always points away from a positive charge, and it always points towards a negative charge. And like I said before, the superposition principle applies as well. So if you have multiple source charges and you will want to evaluate the electric field due to those source charges at point P, you figure out the electric field of the source charges individually, and then you add them together. Again, using, you're breaking them into components, adding the components together, and if you need to, using the Pythagorean theorem to figure out the magnitude and the tangent of the angle to figure out the direction. But again, so vector addition comes into play, and if you don't remember vector addition, now's a good time to brush up on that subject. One way of visualizing the electric field is using what are called electric field lines. So electric field lines come out of positive charges and into negative charges. The number of electric field lines you put on an object should be proportional to its charge. And what you'll see is that the density of the field lines tells you something about the strength of the field at that point, and that no field lines are going to cross each other. And that's one way of visualizing repulsion. So if you see two field lines coming towards each other, they will bend so that they never touch. And again, that's one way of visualizing repulsion. And attraction, the field line comes out of the positive and goes into the negative. We also saw a video on the Millikan oil drop experiment, and this is how we discovered the fundamental unit of charge and what its value was. That you have these tiny oil droplets. Friction gives them a small amount of electrical charge. And as they fall into the air, they reach terminal velocity very quickly. And so from the terminal velocity, you can measure the mass of these droplets. And so if you look, you talked about air drag in physics 1, you know the equation that you would need to do that. But once it reaches terminal velocity, it's then put through an electric field. And so you have an electrical force that's acting upwards on these droplets. And then you have gravity is still acting down. So if you adjust the electric field, so you adjust the voltage, which adjusts the electric field, and we'll talk about that relationship in chapter 23. But you adjust the voltage, you can suspend the droplets or some of the droplets in the air. And so the upward electrical force, QE, is equal to the downward force of gravity, which is the mass of the droplet times small g. And when the object is motionless, there's no air drag, so you don't need to worry about that force once you have it held still. So QE equals mg. And if you know the electric field strength, and you figure out the mass from the terminal velocity before it entered the electrical portion of the chamber, and g is a known constant, you can use those to figure out q. And what Millikan found was that every value of q he got was an integer multiplied by 1.602 times 10 to the negative 19 coulombs. And so that had to be the smallest amount of charge you can have. And that's true unless you're smashing an atom. And outside of high energy collisions in a particle accelerator, you're not going to get a smaller electrical charge than that. So the charge of the proton is equal to positive E, where E is that fundamental unit, 1.60 times 10 to the negative 19 coulombs, and the charge of an electron is equal to negative E, or negative 1.60 times 10 to the negative 19 coulombs. And so the charge in the object is equal to plus or minus capital N times E, where N is the total number of missing electrons, if it's a positive charge, or extra electrons, which is the negative charge. And the last thing we talked about, and this, we're actually going to apply this in the next chapter, but it's worth mentioning here, the electric field, if instead of one point charge or a number of point charges, you have a continuous distribution of source charges. So it's spread out over a certain amount of space, over a line, over a surface area, over a three-dimensional object. So, if there's a continuous distribution, you need to figure out the electric field by integrating over that distribution of charges. So, and here is where the second way of writing the equations is often the easier way. So K times the integral of dqs, the distribution of charges, divided by r cubed, where r is the distance from the infinitesimal element of charge you're looking at to the point where you're evaluating the field. So divide by r cubed, and then multiply by the vector r, where the vector is, points from the infinitesimal element of charge that you're looking at to the point where you're evaluating the electric field. And so you integrate over the entire distribution of the charges, and you get the total electric field. And we'll look at some examples of that when we do chapter 22, which is Gauss's law. And so what we'll see is that Gauss's law gives you the power of turning complicated integral problems into much simpler algebra problems with certain distributions. And we'll show how that works. And then we'll apply Gauss's law further into with some examples that are too complicated to integrate in this course. So, that's the review. If you have any questions coming up to the test, and again, the test is going to be Tuesday the 9th. It's going to be 4 questions. I'm going to post it on Blackboard around 9 o'clock in the morning, and you'll have 24 hours to submit it electronically, and I'll let you submit it via email. And then if you have any questions before the exam, please do not hesitate to ask me. We're limited in this format as far as how you can ask me, but you can send me an email, and if you wish to talk in person, just tell me that via email, and I can arrange a time and a meeting via Zoom, and we can, over Zoom, and we can do that. And otherwise, good luck with the studying and good luck with the exam. And like I said, if you have any questions, about conceptually or any of the problems we did or anything like that, talk to me via email. You can ask me those questions up until the point where I post the exam. But then from that point, you're kind of on your own. Although if you have any questions specifically about the test, you can ask me those. But thank you again, and good luck with the studying and with the exam, and we will talk further.